Consensus is how a permissioned blockchain decides what's true when multiple organizations are writing at once. In this module, you'll see how those consensus choices affect security, performance, and governance, and what that means for mission-critical enterprise and government deployments. In open public blockchains, the primary value is censorship resistance. Anyone can participate. Identities are often anonymous, and transaction finality is probabilistic. That's powerful for permissionless innovation, but it doesn't map well to audited, regulated environments. Enterprise and government systems need something different. Predictable, explainable outcomes that can stand up in court or with an auditor. Permission chains shift the emphasis to authenticated participants, explicit contracts, and accountable governance. Our focus is that shift, using blockchain to move from probabilistic outcomes toward enforceable contractual certainty. When we talk about trust in distributed ledgers, everything really boils down to two goals: safety and liveness. Safety means the ledger story never contradicts itself. All honest nodes see a consistent history, so you don't get double spends or which version is real disputes. Liveness is about progress. New transactions eventually get confirmed, instead of getting stuck in limbo because the network can't agree. For enterprise or government systems, you can think about consensus through two main mental models. Crash fault tolerant protocols assume nodes are honest but may go down or lose messages. Think of Raft or Paxos in traditional clusters. They're optimized for efficiency and availability. Byzantine Fault Tolerant protocols assume some participants can be actively malicious or misconfigured. PBFT and HotStuff fall here. They add communication and complexity overhead, but buy you protection against lying nodes and coordinated attacks, crucial when multiple organizations share control. Byzantine fault tolerance is the paranoid version of consensus. Instead of assuming nodes just crash or go offline, you assume some can act maliciously or arbitrarily, lying, equivocating, or colluding. BFT protocols are designed so the system still reaches correct agreement as long as less than 1/3 of participants are faulty. The trade-off is cost and latency. More messages, more coordination, slower decisions, but in exchange, very strong guarantees for high-stakes use cases like interbank settlement. Leader-based consensus, like Raft, lives in the crash fault-tolerant world. One node is elected leader and orders transactions. Followers simply replicate. That's why message complexity is low and performance is high. If the leader goes offline, followers stop seeing heartbeats, hold a quick election, and a new leader takes over using the same log. As long as fewer than half the nodes have crashed, the system keeps making progress. This model fits closed, permissioned environments such as a private supply chain network with strong operational control. BFT-style consensus is built for adversarial conditions. You assume some validators may be malicious, so you keep the group relatively small and apply a trust but verify mindset. That makes it well-suited to high-value asset transfer across semi-trusted organizations, where finality and Byzantine fault tolerance matter more than raw scale. Raft, by contrast, assumes failures are accidental, not hostile. It scales leader-based replication for teams that already have strong internal trust, which is why it's common for internal audit, tracking, and other single-organization workloads. Settlement finality is about when a transaction is truly done, with no realistic chance of rollback. Public chains like Bitcoin or Ethereum mainnet only offer probabilistic finality. The deeper a block is buried under new blocks, the safer it is, but in theory, it can still be reorganized. That's acceptable for many use cases, but uncomfortable for regulated, high-value settlements. Permissioned BFT networks instead give deterministic finality. Once consensus commits a block, it's final and irreversible, which matches legal and accounting expectations for settled transactions. In a mission-critical enterprise or government setting, forks are more than a theoretical problem. Divergent histories mean two systems may prove different truths, which breaks audits, legal accountability, and automated workflows. Permissioned BFT-style consensus tackles this by requiring a supermajority of validators to sign each block. Only when that quorum is reached does the block become part of the canonical history. Because no single organization can unilaterally rewrite the log, everyone relies on the same finalized sequence of events, a single, durable source of truth that downstream systems and regulators can safely depend on. In enterprise and government networks, the validator set is not a loose group of anonymous miners. Validators are identified, vetted organizations, banks, agencies, service providers, critical infrastructure operators. Each one operates nodes under its legal identity and existing compliance obligations. So consensus is not just technical agreement. It's also institutional accountability. When something goes wrong, you know which entity signed, who is responsible, and which governance rules apply. Quorums define how many nodes must agree before you trust a result. Crash fault tolerant systems like Raft usually need just over 50%. They assume nodes may fail or go offline, but not lie. That keeps liveness high and latency low, at the cost of weaker protection against malicious actors. Byzantine fault tolerant systems push the bar higher, around 2/3. That supermajority gives stronger safety against collusion or bugs, but it also means more coordination overhead and a greater chance the system stalls during outages. Validator management acts like an airlock between governance and operations. Onboarding a new validator should start with legal agreements, then controlled certificate issuance. You're not just spinning up a node, you're granting an institution the power to influence consensus. Configuration changes, like updating the validator set or the Genesis configuration, must follow a governed change process, with approvals, traceability, and rollback options. Offboarding is equally critical. Revoke credentials, recalculate quorums, and verify that resilience and fault tolerance assumptions still hold. In other words, changing a validator is a governance decision that IT implements. In regulated environments, you can't treat protocol changes as ad hoc software updates. Treat each change as a mini public policy process. Someone drafts a proposal with a clear rationale and impact analysis. Then a defined body, often a steering committee representing key organizations, reviews the proposal, checks compliance and risk, and votes according to pre-agreed rules. Only after approval does automation take over. Rollout is scripted, tested, and auditable. The key idea is that governance isn't outside the system. Governance is encoded, and that process ultimately controls the code. Mission-critical trust rests on 4 pillars. First, your adversary model. Be explicit about who you're defending against and how powerful they are. Then choose consensus, key management, and operational controls that actually match that threat. Second, finality. For legal settlement, you usually want deterministic finality, with clear rules about when a transaction is irreversible. Third, governance. Define transparent, documented processes for changing code, parameters, and membership, including emergency procedures. Finally, resilience. Design for liveness under failures and attacks, redundancy, monitoring, and practiced recovery drills so trust doesn't disappear when something breaks. To close, carry forward 3 big ideas. In enterprise and government settings, trust is distributed, but identity is not anonymous. Cryptography gives integrity, while strong IAM and PKI tell you who you're dealing with. Next, choose consensus that fits the threat model. BFT when you expect adversaries, Raft when you prioritize internal performance. And finally, deterministic finality underpins legal and regulatory certainty.